Hi everybody, welcome back to Chem 161 here. I'm talking over lyrics here, hold on. Some of the songs in the soundtrack are just strange. I think I might have spoiled myself because I'm playing this game right now. And I'm like, I don't recognize these characters. I think I do. Weren't they nice? And then this song plays, and I'm like, oh, they're probably going to try and kill me. Good to know. And I think I'm right at that part of the game anyway. So, oops, that's what I get for playing a soundtrack of a game that I'm playing right now. Um, we need to talk about the lab. But first, I want to get these problems out of the way because this is what I left you with yesterday, was to do these problems. Now, hopefully you did that, but if you didn't, while I get all of the windows set up for the lab, um, I'm going to give you like 2 or 3 minutes just to do them. Calculate these expressions to the correct number of Sig Figs so that your result accurately reflects the steps that you took. Okay, make sure you follow order of operations, and we'll go over the answers in just a moment. See you in a bit. Maya's here. She says hello. Oh my. One more minute. We'll go over the answers. Meow. All right, so let's go over these answers real quick. I got to capture this window. Oh, I guess that was already pretty good. Huh? There we go. I need my pen. There we go. All right, so for this first one, I don't actually need to work on the Photoshop down below, but what I'm going to do is I'm going to type this into the calculator. So 0.0019 times 21.39, and I'm just going to write down the number that it gave me. Oops, apparently I'm not. There we go. So 0.040641. Now, I need to check to see how many Sig Figs each of these numbers has, because when I multiply, I want to have the result also have the fewer number of Sig Figs. So this one has 2, and it's just these 2. This one has 4 Sig Figs. 2 is fewer than 4, so my answer should have 2 Sig Figs, which means that I want to keep not these first 2, because 2 numbers multiplied together don't just give you 0. That's no good. So I need to keep taking actual Sig Figs. It'd be these first 2 right here. And so I would get 0.041, because I'm going to round up. So there's the first answer. For the second answer, I'm doing the same thing. I'm doing division, but it's the same rules. So I'm going to just copy down what the calculator tells me. 20295122195. That's a lot of digits, and that's just going to go forever, probably. How many digits do we actually get to keep? Well, this number is 4 Sig Figs. This one is 2. So my answer gets to have 2, which would stop me there. And we write, this is our answer, 2.0. Now Maya's meowing at me from the hallway with her loud, meow, you aren't petting me. Maya is one of those cats where I always have to be petting her, or else she is just sad and nobody loves me. Oh, maybe all cats are like that. On number 1, if 0 take the highest... Can you explain what you mean by that? I'm not sure what you meant by if 0. I'm going to set up the next problem here. I realize I'm talking from the future here, somewhat. So if I do my addition here, this is what I should get. And then when I do my Sig Figs, we're going to start from the right. I'm going to look in each place. I'm going to see if there are all Sig Figs in this column. It turns out for here, there's not. Don't get to keep that number. Here, there's not. Don't get to keep that number. Here, there's not. Don't get to keep that number. Now I get over here. 3,000. The only Sig Fig in 3,000 is this 3 right here. So I don't get to keep this number. I should have gone this way, actually. Or this number. Or this number. I'm going to round to this position. And that's the answer I would report. Oh, for that number. Okay, so these zeros right here, let me get the highlighter. These zeros right here are not Sig Figs. Those are placeholders. Because if I were to remove those, that number would change from 0.040 to 40. That'd be a very different number. So I need those zeros to get the magnitude of that number right. But they are not significant figures. Remember the decimal rule, that anything to the right of all of your digits is a sig fig, so anything over here would be significant. But anything to the left is not. Let me get the rest of these on the screen here. So this is a subtraction problem. So there's me doing the subtraction. That's the number that we get. Now I have to check for Sig Figs. So we're going to start from the right. Does this position have Sig Figs in every value? And it totally does. So we get to keep that. And so this is actually our answer. But what you'll notice is that the number of Sig Figs that we have in this result is fewer than what we started with. That's a thing that can happen with subtraction. Addition is the same way. You can actually gain Sig Figs by adding numbers together. So addition and subtraction don't care about how many Sig Figs you have. They care about places. So just be really careful when you're doing these operations that you aren't making any assumptions. The next one is a concept check, because we can all multiply 6 times 2, right? It's just 12. But when you punch it in your calculator, this is all it spits out. How many sig figs should you have? Well, since each of these has 4 sig figs, because these zeros all count, they are to the right of a sig fig in a decimal. They are all 4 sig figs, which means that our answer should have 4 sig figs as well. So I need to actually insert 2 extra digits, and that's my answer. All right, let's do these last combined problems here. So this first one, I need to actually do the addition first, because that's what's in the parentheses. So we'll set that up. Oops, not like that, we won't. That's not how we add. There we go. That's, wow, that 4 was really, really wide. There we go. All right, and then I need to check for sig figs, and you should notice pretty quickly that these aren't going to work, so I don't get to keep these numbers, because there's no digit there. But I do get to keep this and further, because there are numbers on every position. So the result that I would import into the parentheses would be 41.5. And so my new expression becomes 41.5 times 0.00390. And if I'm checking for sig figs, each of those has 3 sig figs, because these are 3. And then in my decimal, there's my 2, and anything to the right counts as well. These zeros in the front are placeholders. All right, so I multiply it all together, and the result that I get should have 3 sig figs, and that result is 0.162. And then for the last one, we're going to do the division first, because it's in the parentheses. And what I get when I do the division is this: 14.58333 forever, basically. But how many sig figs should my answer have? So the top has 6 here, but this only has 2. So my answer should have 2. And so I report my answer as this: 15. And then I gotta do this part, which I almost forgot, actually. And there's my answer. Now, if you're doing round to even, you might get a different number than me. We're not doing round to even in this class, so no bankers rounding. All right. That's the practice problems for sig figs and arithmetic. Let me know if you have any questions. Next thing I'm going to do is I'm going to talk about the lab really briefly. I will once I find my phone. Where did it go? My phone just sits next to me, so I have a timer on the screen because it's not always showing. All right, so let me get that window here. Yeah, here we go. I just got to scroll this all the way to the top. Excuse me. All right. I'm going to cover up the chat for just a little bit. All right. So for the first experiment, what you're going to be doing is you're going to be using the idea of Sig Figs to do some calculations on glassware to show which glassware is the most accurate. Now, I have already made the measurements for you by going into the laboratory and doing all of the calculations. Or not calculations, I should say. I should say the data. And you're going to provide the calculations for me. So the way that this works is first you need to know what the glassware is. So it's important that you read about the glassware because different glassware is used for different things. For example, a beaker and a graduated cylinder are low accuracy because they have marks that are every, like, say, 10, or on a graduated cylinder it might be every 1. But a pipette or a burette are much more precise because they have more marks, or the pipette just is specifically calibrated to deliver a certain amount anyway. So make sure you are understanding what the glassware is by reading about it. All right. What else do we have here? So yeah, this is just reading about stuff. Don't put pipettes in your mouth. Believe it or not, that was a thing a long time ago, is people would pipette by mouth, and they would occasionally suck chemicals into their mouth. Then you're going to get to this page. This is pre-experiment questions part A, and it's going to ask you a bunch of questions, and you're going to have to fill these out. The way that you do that is you go over to this that hasn't loaded yet. Wait, what? That's not what I had. I clicked on the wrong thing. Hold on. I thought I had clicked on the Google Sheet. The screen's going to look a little bit weird for a second. There we go. And so now that you have these questions available, you can then answer them in the Google Sheet. Now, in order to access the Google Sheet, you are going to have to go to the Modules tab and click on this module right here. I gotta move this over. How to upload completed worksheets in Canvas. Make sure that you follow those directions to acquire your own copy. It's basically, you click on share, or not share, I'm sorry, make a copy to your shared drive or whatever it is. And then you're going to download an XLSX file once you are finished with the documentation. Do everything in Google Sheets. If you do it in any other program, I may not be able to open it, and you may not get a score. So be mindful of that. Please follow these directions to access and complete the form. Once you're in here, you're going to just fill out the answers to the questions based on the information that is in the lab. That's straightforward enough. There are quite a few questions, so make sure you're scrolling down. And then when you're finished, you go down to the bottom here and you click on the next tab. And here, what you're going to see is the data tables for the experiment. So this is the data tables for the glassware. So we're going to use a 150 ml beaker, a 100 ml graduated cylinder, a 10 ml pipette, and a 50 ml burette. Now, what this data is trying to get you to do is to compare the amount that was measured out based on what the lines on the thing tell you. That's why it's the observed volume. Versus the volume of water that it actually had using the density. And so we need some information to do that. All right. That information is at the start of the experimental section right here. For all experiments, the temperature of the water is 22 degrees Celsius, and the density of the water at this temperature is right here. Make sure that you have that number handy, because the way that you're going to get the calculated volume is in this manner here. So let me just move this over. here's how you're going to calculate volume. So, for example, for the 50 milliliter beaker, we're going to fill it to this line. And I guess my water's... Now we'll just change the color. It's like, I guess my water's going to be pink, huh? So we're going to fill it to this line. And so we're going to say that the observed volume is 50 milliliters. Note that I put a dot there. That's going to be important later. Then what we're going to do is we're going to take the sample and we're going to put it on a balance. Or something like that. I mean, I better put a number in front so this is reasonable. Now, from this information, you are going to get the mass of the water in the beaker. Now, obviously, you need to have done some steps before this, so you would have had to have weighed the beaker before putting this on there. And then you would get the mass of the water by difference. And the way that that would work would be, well, if you know the mass of the water and the beaker, and then you weighed it before with just the beaker, if you subtract, those would cancel out, and you'd be left with just the mass of the water. But I don't want to draw all of those steps, so we'll leave it that way. Once you know the mass of the beaker, you already know the density of the water, and you know, or not the mass of the beaker, the mass of the H2O in the beaker. You know the mass of the water, and you know its density. You could solve for the volume, and the volume that you get that will be the volume from a calculation. This is what we would consider to be the actual volume. So you thought it was 50 because you poured it out and measured it against a line, but in reality, it was whatever this is. So now what we're going to do is we're going to say, okay, well, this is the volume that we measured. And this volume down here is the volume that it actually was. And so when we go do percent error here, the percent error, which the formula is given in the documentation here, would be volume measured minus the volume that it actually was, divided by the volume it actually was, times 100%. Now, if these numbers were the same, I measured out 50 and my true volume was 50, I would have 0 divided by 50, which would be 0% error. If I have any deviation from that true value in the measured value, for example, if I measured 50 but the true value is 47, then I'm weighing out too much. I will have 50 minus 47, which is 3 over 50, or 6% error. A common question that I get a lot of the time is, what happens if my percent error is positive or negative? If you have a positive percent error, the amount that you measured out was too large compared to the correct answer. If you have a negative percent error, then the amount that you measured out was too small compared to what it actually was. So if I measured out 50, but the beaker actually had 52.7 milliliters in it after doing the calculation, then my percent error will be negative because I'm consistently getting too little water if I'm measuring to that same mark every time. So that's what percent error means. A lot of people see formulas for percent error with an error with absolute value bars on it, like this. And I actually think that that's bad because you're losing information. The sign tells you something. So do you report the sign with your percent error if it's positive or negative? That is important. All right, that's the gist of experiment 1. If you have any questions, let me know. All right, when I say experiment 1, I mean experiment 1 part A. There's a part B. And part B is going to have you plotting data on a graph to get the density of sugar. And your graph should look something like this when you're done. And so what we're going to do is we're going to collect data, which I've already done for you. You're going to determine the density of the solutions based on their mass and their volume. You can do that. That's pretty easy. And then what you're going to do is you're going to plot this data on the graph. And I've given you instructions to do this. But what we're going to do is I'm going to show you more or less how to do this. So here's our data tables on here. And then it says, use these columns for your graph's data tables. So you're going to put some numbers in here. So we're going to just make some random numbers up. Let me make a copy so that I'm not editing something with you guys as you are downloading it, because that would be weird. And I actually want you to be able to see that up there at the top. All right, so this is this section right here. So we're going to make just a generic data table. So I'm going to say, like, this will be number of students in class, and then this column will be number of cookies they deserve. All right, so if nobody shows up to class, nobody gets any cookies. Oops, I put that in the wrong column. There we go. If 5 students show up to class, everybody gets a cookie. If 10 students show up to class, I'm going to give everybody 3 cookies. And if 15 students show up, I'm going to give you 7 cookies. And then if 20 students show up, I'm going to run out of cookies. So, all right. This data is totally nonsensical. Nobody would plot this. But now what we want to do is we want to make a graph out of it. So you go to Insert, you click on Chart, and the system's going to try and plot the data, and it will always do a bad job. So ignore what it's done and go straight over to where it says Column Chart, which you can't see because I got to make this smaller. There we go. Go over here to where it says Column Chart, and you want to scatter plot. Anytime you do graphs in this class or any chemistry class, you're always going to do a scatter plot. And it's still not really going to know what to do because it's just putting data where it thinks it goes. So it's trying to bin your data. And what that means is that it's just going to put it equidistant from one another. So what we need to do is we need to actually select the data. So on the x-axis, we're going to click on this, and then you click on this box right here. This is select a data range. And now you can select your data points. I'm just going to select the numbers. There you go. And then for the y-axis, I want this data. And now my data is graphed correctly. Although I am noticing that, like, my 0 wasn't included for some reason. So let me try and see if I can fix that. So, x-axis, minimum value, 0. Yeah, it didn't show up for some reason. Oh, what is going on? What on earth are you doing? Ooh. Oh no. Is one of my keys stuck? That was weird. Sorry, my system went crazy here. So x-axis should be... Wow, I don't know why it changed all of my stuff here. This is so bizarre that it's not working. But of course it doesn't work the time that I set it up, right? All right, there should be a point at the origin. I don't know why it's not showing that point at the origin. So on our graph, what are we supposed to do when we have items without a designated value for x? So if you're referring to your unknowns, you do not plot unknowns on your graph. And the reason for that is because they're unknown. You don't know what they are, right? I have a feeling that it is plotting 0, 0, but it's not actually showing. So the way that we can check that is that if we go to the horizontal axis, I'm going to make the minimum -1. And then for the vertical axis, I'm also going to make the minimum -1. And there should be a data point at the origin. There's totally not. Yeah, why is it not plotting this first data set? Google. Oh, for fuck's sake. Maybe it wants me to actually put the title in there. There we go. Now I actually have data in that column. Okay. So include the title if you have one. There, that's what it's supposed to look like. You know, it wouldn't make me do that, Excel. All right, so now what I'm going to do is I'm going to play with these axes again. So I don't actually want this negative space at the bottom here. So you could play around with the axes here. Boop, there we go. That looks pretty good. So now the next thing that you need to do is we need to have a trend line. We need an equation that describes our graph. And now obviously this isn't a linear equation, but let's just pretend that it is. So you're going to go to legend here. And what you're going to do... Is it not in legend? Maybe it's in series. Here it is, series. You're going to click on this, trend line. Boop. And it's going to put a line right through your data for the line of best fit. Now, the line by itself is not useful. You need an equation for it. So you're going to scroll a little bit further down. Under trend line, you're going to select use equation. Loop, there you go. There's the equation. And then you're going to click on show R squared. What this shows you is that this is the equation, so that for every student in the class, I award about 0.277 more cookies. But everybody gets 0.244 of a cookie for free, I guess. That's the equation that is modeled by this relationship. Now, this number over here, R squared, 0.647, this means that our data is sort of linear, but not really. The closer this number is to 1, the more linear it is. 1 would be a perfect line, whereas 0 would be there is no linear relationship you can make at all. Every linear fit that you apply is equally bad. And then what you can do is you could say, okay, well, now I have this equation here. So maybe the experiment is saying, well, if you gave out 5.5 cookies, how many students would be in the class there? Well, now you can import this into your equation. And I can say, okay, well, if this is y equals this expression, and I set this equal to y, I can now solve for x. So you're going to be doing that for your unknowns in doing a calculation. So use the line of best fit to solve for your unknowns. Don't plot them. They are unknowns. So never plot your unknowns. They're unknown. You don't know what their concentration is, right? So you cannot put them in the graph. But what you can do is once you have your standards in the graph right here, you can then you can determine your unknowns because they will follow the same relationship regardless of where they fall on the graph on the x-axis. Once you've got that graph and you've solved for the concentrations of the unknowns in the Pepsi and the Diet Coke or whatever it is they give you, then you have some more analysis questions. A common issue that comes up with students doing these calculations is they don't know where to get the actual stated amounts on the can. And so the way that we're going to do that is here are the labels on the soda. What you're going to use is you're going to use the volume of the soda. The volume of the soda is 355 milliliters because that's just the standard that we do for cans, 12 fluid ounces. And then you are going to do the amount of sugar in there is listed where it says sugars. So right here, there are 41 grams of sugar per can. So you can find a percent sugar in grams per milliliter. For Diet Coke, well, it's Diet Coke. How much sugar is in Diet Coke? Well, there's nothing, right? So there's 0 sugar for 355 milliliters. So you know what its percent sugar is. And then you can calculate percent deviations based on what you got from your calculations. Note that 0 is kind of difficult to do a percent error for, so your percent error will be undefined for Diet Coke. But for Pepsi, you can calculate a percent error. And there you go. At the end, I tell you the scoring breakdown. The scoring breakdown is also listed in the worksheets next to each question. And so you should be good to go once you've filled out everything and followed all those directions. You can just check this to make sure you've done everything. All right, that's lab number 1. Let me know if you have any questions on lab number 1. Now, as you can see in the experiment, and I still have the experiment here, so we'll just go back to it really quickly. On all of these experiments, what I had done was we had taken multiple trials. How do you submit it? That's all in that documentation on how to upload your files. So an assignment will appear on Canvas, and then you upload your .xlsx file to that. Follow the documentation in the module right here, and it'll tell you how to do that. You'll notice that in our experiments, we do multiple trials. And the reason that we do multiple trials is because no one trial will be 100% reliable. So you might have different types of error that occur. So you might actually make a wrong step in the procedure, or maybe you're just not great at lining it up on the line and you're going to randomly be too high or too low. So a good way to try and minimize the amount of error that we have is to take the average of a bunch of trials. So in this next section, what we're going to discuss is what types of error are possible and how do they affect your results and how can you eliminate them if possible. So on the screen, I have calibration data for cough medicine delivered into 10-ounce bottles. And so the dispenser is programmed to deliver 296 milliliters every time. However, due to things like wear and tear, or maybe a blockage in the container, or it hasn't been cleaned or maintained or something like that, you're going to get random errors. The first thing we want to do is identify the nature of the errors based on what we are observing in their data. So if the target is 296, which I'm going to circle up here, and we look at this, we can make some conclusions. This is under-delivering by 10 to 13 milliliters every time. That's 5% off. That's significant. If you went to the gas station and paid $60 for gas to get 20 gallons or whatever, and they under-delivered you 5%, that'd be an entire gallon of gasoline that you did not get but paid for. That's significant. So we would consider this data set, because it's so far from the target answer, to be inaccurate. So this has low accuracy. What is the threshold for accuracy? It depends on really what you think it should be. 5% is a good cutoff. Like, if you're above 5%, you are certainly not accurate. Now, what about the quality of the data points themselves? Is the machine dispensing the right amount every time? No. But is it dispensing the same amount every time? And in this case, we could say, oh, okay, well, these are all off in just the last digit, except for this one erroneous one. So these are very close together in terms of their value. So we would say that this data set has high precision. Accuracy is how close you are to the correct answer. Precision is how close you are to other data points. Precision can also be percentage-based, but I prefer to just eyeball it. Looking at your precision, you can tell really quickly. If it changes in the last digit, and that's it, you're definitely going to have high precision. And then if it changes in the last 2 digits, but only very, very slightly, you're okay to mark that as high precision. You'll know if something is low precision because look at dataset number B. My range goes from 293.9 all the way up to 298.3. So I have a deviation of 5 there. That's quite high. So this is low precision. However, if I were to take the average of all of these numbers, so I'll just punch them in the calculator, 298.3 plus 294.2 plus 296.0 plus 297.8 plus 293.9. I mistyped. And then I'm going to divide by 5, and the average that I got was 296.04, which I really only get to keep this number because I'm doing addition here. But you'll notice that the average is exactly where it needs to be. So this has high accuracy because it was very close to the true expected value. Data set 3 over here is both high accuracy and high precision. So dispenser number 3 has been recently maintained or is new or something. It is doing everything correctly. But dispenser number 1 has been miscalibrated, and dispenser number 2 has something going on. Maybe there's like something that is blocking the nozzle and just causing it to dispense a wider range of medicines. So by looking at our accuracy and our precision and our data, we can actually make discoveries about what's going on behind the scenes. So if you look at your data and you're like, wow, my data is really precise, that means that you've been doing the experiment correctly. But if your accuracy is low, that could tell you, oh, well, maybe I made a mistake in one of these steps, and then you can go and try and find what you did that was wrong and possibly correct it. All right. So there's our definitions there. So data that is precise is very close to other data points, whereas data that is accurate is close to the correct answer. I do have a visual for that. I gotta find that visual. We'll come back to this in a second. There it is. So if you are a marksman, either in I don't know, with a firearm or like archery. I did archery in high school, and it's super fun. But it's also really hard because it's very difficult to be precise without a lot of skill. First-time archers, if they hit the target at all, end up in these categories right here, where you just hit the target and you hope for the best, right? We would say that the top data is not precise because there's a lot of deviation between my shots here. And I can show that by just drawing a shape that connects all of these. The larger the shape is, the lower my precision is. Now, if I take the average by just kind of doing this and figuring it out, I can then compare how far away I am to the center of the bullseye to determine accuracy. On the one on the left, not very accurate, but the one on the right here, that's pretty good. If you were doing this at the range on your first day, that's pretty awesome. Now, if you're an expert, you start to do the same thing every time. And so you get very similar results every time. Now, again, taking the average, I'm significantly far from the bullseye, so this marksman is not accurate. This marksman has an error with their equipment, but they're doing something correctly. What would that error be? Well, maybe their scope is not sighted properly. But they're doing the right technique, like they're exhaling and then pulling the trigger and then exhaling, or whatever it is. I've read all about this because I did a chapter in a novel about people at the firing range. This over here, if you take the average, you land right on the bullseye. This is my level 20 orc gunslinger who has all his points in pistols, basically. You hit the bullseye every time. So this is obviously what you want to be, but in the laboratory, this is what we would accept. Like, this is what I would have you aim for. Try and be precise, because that means that you are doing the experiment correctly, and that we can diagnose minor issues. Oh, you didn't hit tear. That's fine. At least you did all the other steps correctly. If you just make random errors everywhere, you get this as your result, and that's no good. So we don't want these up here. We want precision. All right, let me go back to these slides that we skipped so we can talk about these last things, and then we'll probably be ready for a break. Now, depending on how you use your tools, just like with the archery and the revolver example, if you misuse the tools, you misinterpret the correct answers. With a graduated cylinder, the same practice is very possible. For instance, if you are looking at a graduated cylinder, but you're looking at it from the wrong direction, what ends up happening is that if you measure where the meniscus is, but you're standing at an angle, you end up thinking that it's higher or lower than where it actually ends up. Now, this is very possible to happen in the lab because we're not all the same height. If I put a burette on the bench top, this is actually a burette because notice that the numbers are counting downward. If I put something on the bench top and I'm 6 feet tall, I can see it at eye level, but my lab partner who's 5'6" might not be able to. She'd be looking at it from below, and all of her numbers would be too large. Then if I adjusted the height so that she could read it, then I would be unable to read it correctly because now I'm looking down at it. And so what I would have to do is stoop to look at it correctly. Not everybody does that, though, because you don't think to. Like, oh, do I need to crouch down a little bit to look at it head on? That's actually the proper technique. But if you didn't know that, that would be an issue. So what type of error is this? This is called a systematic error. If you make a systematic error... Oops, that was a really bad line. If you make a systematic error, you are making a procedural error that affects the accuracy of your data. But the precision may still be retained if you keep making this error. Now, if we have like a number line here, so let's suppose that this in the middle is the correct answer. But I keep looking at this from below and getting a number that is consistently too large. And so here's all of my data. Here's all my data. If I take the average, I'm going to just land right in the middle of my data. And so if I have this issue, I cannot average it away with multiple trials. So systematic errors cannot be averaged away. So if you make a systematic error, your accuracy is just done. You are off of the correct answer. And there is no way to fix that other than chance. But what other types of error are possible? Well, there's also the possibility of random error, which comes from random sources. For instance, if you were measuring liquid into that same graduated cylinder of urette, and you wrote down a number, but your lab partner wrote down a slightly different number that was still within the tolerance of what Sig Figs should be for that piece of glassware, you're going to get slightly different answers, and your answers will deviate from the correct answer, not off in one direction, but in a random direction. Sometimes your number will be slightly higher than the correct answer, and sometimes your answer will be slightly lower. What other things can affect random outcomes of your experiment or your data? Things like temperature. If you're in a room that has a heater that is constantly kicking on and off because it's cold out and it's trying to maintain the temperature of the building at 70 or whatever, or maybe you're in a laboratory where there's high ventilation, and so it's changing the pressure of the air around you. Whenever the ventilation system kicks on, the pressure increases in the room because there's now more air being forced into the room. As opposed to when it turns off, then it goes slightly down. If you're working on an experiment with gases that day, that would be important because pressure affects gases. These are all sources of random error because they affect your results in a random direction. If I take the average of all this data, so let me just put some more data here, I would end up in the center of that data, and I would average it away. So random errors can be averaged away. Now, fortunately for us, systematic error is avoidable and random error is unavoidable. So if you do the experiment correctly, you will not have systematic errors, you will only have random errors. And then, if you do the experiment multiple times, you can average away that random error and have even less of it. So the more trials you do correctly, the closer you get to the true correct answer. So that's the philosophy behind experimental technique. We do experiments multiple times so that we minimize random error in our results. All right. We've already talked about how to average stuff away. So our goal, again, in the lab is to be precise and accurate. But the goal of learning how to do experiments in the laboratory, and again, I'm sort of saying this as if we were going to the lab. You will in 261, and hopefully soon when we eventually go back into the classroom. When you get into the laboratory, you will want to do things multiple times. One, to make sure that you're doing it correctly, just to get practice. But two, so that you'll be able to average away your random error. Now, in the laboratory, if you are doing an experiment and you're like, oh, wow, that experimental data point is obviously wrong because it's way off from all the others, note that in your discussion and then omit it. You're allowed to remove data points if you can justify why you're doing that. If you say, like, oh, for trial 1, I didn't hit tare, so it was 5 grams too high, and everything else looks fine, then don't include trial 1. That's okay. All right. We're going to go on to the next section, but first we are going to take our break because that is what time it is, I believe. My phone keeps turning off its display. 12:55. Yeah, it's time for a break. Why are we not doing labs in person? We're not doing the labs in person because Mostly because the instructors don't feel comfortable with it. And also because I have 90 students in this class, we do not have lab space to both safely socially distance and also get everybody on campus. And then I think the third reason actually would be the number of hours that they would have to pay faculty to go to the lab. I don't think the college could afford all of that right now. So there are so many reasons why we're currently not doing labs. In our department, we are only running organic labs. And of those organic labs, I believe we use all 3 of the rooms. And we actually have very little space. If you're in physics, are you in Christine's physics class? Because I think she's doing, like, outdoors experiments and stuff, like with liquid nitrogen and cool things like that. Let me put the timer up here. If you can do your experiments outdoors, then you're in great shape. And I think that there is totally justification for doing that. But we absolutely cannot do chemistry outdoors. I wish that we could, but we cannot. All right, I'm going to put on more Bravely Second music, if I can find the right track to start on. There we go. All right. I will start the timer, and we will see you in about 10 minutes. Hi, everybody. Sorry, I was just finishing an email really quickly. Scroll this down. All right, let's get back to it. So we're going to finish the rest of Unit 1 today. What slide are we on? Let me see here. Yeah, we'll very easily do this. Okay. This last bit is just how do we do math using Sig Figs and doing unit conversions. You have all done unit conversions, so I know that you are capable of turning grams into kilograms or inches to feet or whatever, but we are going to show some examples of how to do that. Just for practice here, just to make sure that we are all on the same page. So I'm not going to explain the philosophy behind dimensional analysis here, but we will just show it by doing, more or less. Oops. All right, so if I have a 6.8 kilogram bowling ball, and I want to figure out its mass in grams, I could form a relationship between kilograms and grams like this. 1 kilogram is equal to 1,000 grams. So I can set up this relationship to do dimensional analysis by creating a relationship like this or inverting that. And I'm just going to select the relationship that I want to cancel out the units that I don't want. For instance, over here, I have kilograms on top of the expression. So if I put a kilograms on the bottom down here, they would cancel, wouldn't they? So let's do that. I'm going to use this expression because it has kilograms on the bottom and grams on the top. That will allow me to get an answer in grams. And then I just fill in the numbers. So 1 kilogram is 1,000 grams. And there you go. So very simple dimensional analysis. We are capable of doing that. All right, let's do the next question here, which is how much does the bowling ball weigh in milligrams? And we can do the same sort of procedure here, where I say, okay, well, now I have my bowling ball in grams. I can turn it to milligrams because I know that a milligram is equal to 10 to the minus 3 grams. So let's take our bowling ball in grams. And I'll just set up the units to make this relationship grams, milligrams. There you go. The grams will cancel out. And I'll be left with milligrams as my answer. I like to do the units first, and then I do the numbers, just to keep your brain on thinking, okay, what units do I want to get to the end? So then we just put in the numbers here. And there you go. All right. Any questions, let me know. These are very basic calculations that we should be able to do. Now, on the bottom here, I have a note that says when converting to metric units that are not the base unit, go through the base unit anyway. We actually did that. So if you had started with kilograms and we're doing this problem, then my recommendation for your path is not to do this. Don't do this directly. Instead, turn kilograms into grams and then into milligrams. And the reason for that is because the metric chart that you have been encouraged to memorize, but don't have to because it's an online class, has references that are only valid for transitions through the base unit. And if you go from one prefix to another, you have to start doing crazy stuff with both memorization and then mental arithmetic. Don't make it harder than it needs to be. When do you want us to use scientific notation? Whenever you feel like it is necessary. Obviously, don't write 16 zeros after your answer. You can see that when I wrote my answer, I tried to block my zeros in groups of 3. So, like, there's a space between the first 3 zeros and then the 800. As the 800 written as 800,000, and then there's kind of a space between the 8 and the 6, but not as obvious a one. I try and group mine in groups of 3 just because it makes it easier for counting. Oops, that's the wrong one. We're not going there yet. All right. Now, if you have different units that are not metric to metric, for example, Imperial Metrics, so I have this orc here. I actually have this statue in my living room. Not statue, I should say. It's a figurine. And I have the mass of this character, and I want to find the weight in pounds. What would I do to do that? Well, I could set up the same sort of decision tree here and say, okay, 1 kilogram equals how many pounds? And I can go look that up, and it's this. And then I can do the calculation. First, we'll set up the units so that the units cancel. And then we'll do the numbers. Now, when we're doing this sort of calculation, we do have to consider Sig Figs for the conversions. We didn't do it in the previous one because all of the conversions were exact, so the number of Sig Figs I put in is how many I get out. Usually, the number you're starting with is going to dictate it, but in some cases it won't. If you see a 1 in a conversion, 1s are always exact. A 1 never governs your Sig Figs because that is exactly 1. In exactly 1 kilogram, there are approximately 2.205 pounds. That's how that reads. And now you can do the calculation, and I actually have this answer memorized, so there you go. Oh, my text appears beneath it, but that's okay. All right. So what I want you to do is I want you to try to do these basic calculations. Now, obviously, these are units that are common, and you can look them up on Google. For example, if you type in 579 pounds to kilograms, Google will do that for you. How am I going to test you on stuff? I'm not going to use units you can Google. I'm going to just make up units, like a squip, or a jolt, or whatever. And, like, I will assign some arbitrary amount to that and be like, okay, a squip is 13 inches. How many squips are there in 74 miles? And that will be a very different calculation than if I said, okay, a foot is 12 inches, in terms of your ability to go look it up online. Okay, so go ahead and do these problems, and we'll go over the answers together in just a bit. Once you have the answers, go ahead and type them in the chat. I'll give you about 2 more minutes. All right, let's go over the answers here. I gotta clear all this out. All right, so when we're doing these problems, if the first thing you need to do is find the relationships that you need. So for this first problem, we need miles to kilometers. And so we need to look up a relationship between miles and kilometers. And so if I look this up, I get 1 mile is 1.609 kilometers. But you could also go the other direction and say 1 kilometer is like 0.621 or something miles. And that totally works. You can use either one. You get the same result. Then I'm going to convert from miles to kilometers, setting up the units so that I cancel out the ones that I don't want. This leaves the units that I want. Now I can do the numbers. So it was 1 mile, boop, 1.609 kilometers. Boop, there you go. And you should get something like 33, I think. Oh no, I can't math in my head, sorry. 24.9395. I was thinking of pounds, that's what I was doing. This is 3 Sig Figs, this is 4 Sig Figs, this is infinite. So our answer should have 3 Sig Figs. There you go, that's the first one. No problem. Uh-oh, that's not the first one. My problem just captured the second one. That's okay. That's the second problem. I skipped over the Harley problem. So let's go back and do that. Oops. Transposing my numbers here. Don't mind me. This is how much my motorcycle weighs. I do own a Harley. I haven't ridden it for a few years, though, because I bought a Jeep. I love my Jeep Wrangler, and it's so much more practical, but I really miss my Harley on days like this. We're going to turn this into kilograms, which means I need a relationship between pounds and kilograms. And a kilogram is, what, 2.205 pounds? So I'm going to set up my units so that they cancel out. And I want my answer to be in kilograms. There we go, we're all set. So let's do the numbers. 2.205 pounds, 1 kilogram. There you go. There you go. That's how many kilograms that is. And this is 3 Sig Figs. This is 4 Sig Figs. Exact. So our answer should have 3 Sig Figs. There you go. And then the last problem, we have our 2-liter soda bottle. Notice that 2 liters is just 1 Sig Fig. Can you take a guess on which direction they shortchange you when they print 2 liters of soda? Because 1.55 rounds to 2. 1.7 rounds to 2. Might be an interesting experiment to measure at and see if you are actually getting 2 liters of soda. My thought is you were actually getting pretty close to 2 liters, but I would bet that it would be slightly less. So I need to turn liters now into gallons. I did this in the wrong color. Let's try this again. And I gotta look this one up because I don't know it off the top of my head. 1 gallon, 2 liters. 3.785. All right, I can cancel these out. Now I can do the numbers. So 1 gallon, 3.785. And I got 0.528, but I only get to have 1 Sig Fig. Because this number is 1 Sig Fig. And then for the last problem for microliters, I don't really need to write out the little blueprint here because we can just do this right away. We'll just use a metric prefix here. 1 microliter is 10 to the negative 6 liters. I get 2 to the positive 6. We don't ignore conversion factors in Sig Figs for conversion factors if they are the ones that are the smallest. But in this case, this 2 right here is the smallest. This is 4 Sig Figs, and then this is infinite. So almost all cases, our conversion factors will not affect our result. But in the event that they do, you should consider them. It will be rare that a conversion factor will affect your Sig Figs. All right. Now, these are very simple problems. Obviously, we need to up the complexity of the problem so that we can be equipped for more probable situations that will come up. Because you're not going to be given, like, a complex task where you're just converting length, right? You're going to be given things where you have to convert units to interesting and weird dimensions. For example, if Maya meows once every 2 seconds, how many times will she meow in a year of me owning her? And the answer is an insanely large number. Maya, please stop. I'm going to have to squirt bottle her. All right. So to solve weird problems that have odd or unusual conversions, what you're going to want to do is start with the number that is given to you as a constant. And in almost every problem, you're going to have an obvious number that's just kind of orphaned or by itself. And in that problem, there will be some other relationship that will help you solve it that information can be used to construct what I call a unit map. So we've already been kind of doing the unit map, which is just the thing that I've been doing to the side over here. It's this sort of thing. If you just plot your course and then start writing conversions through your unit map, this will help you figure out where you need to go to solve the problem, and then set up the calculation once you're done. So let's do a simple example that doesn't have a conversion, but just has a, oh, I have to take multiple steps to do this type of scenario. So if I were to do this problem, how many hours are in 2 years? So I'm starting with years as my time, but my goal is to get to hours. I don't know how many hours are in a year, but what I do know is how many days are in a year. And I know how many days are in, or how many hours are in a day, right? So I can do this map here. For each of these arrows, this is going to be a conversion. So I could say that in 365.25 days, that would be 1 year. I'm doing the 0.25 because I don't know if it's leap year or not. So we'll just use the solar year. And then in 1 day, there are 24 hours. So now I have a chart, and I'm going to start with years, and that's the number I was given anyway, so let's do that. So I'm going to start with 2 years. I'm going to do all the units first, so I'm going to turn years into days. And then I'm going to turn days into hours. And that's the unit I want because that's the answer to the question. Okay, now we've done all the units, let's do the numbers. There are this many days in a year. And there are this many hours in a day. Everything is all set up. We can now punch it in the calculator. And I got that many hours. How many Sig Figs should my answer have? Well, this has 2 Sig Figs. This is 5. Infinite. And this is actually counted. So my answer should have 2. There you go. So these problems are starting to get slightly more and more complicated as we give you dimensions that are farther and farther apart and require more and more conversions. Let me clear my text off the screen there. All right, so let's give you some more practical problems that have more unusual conversions in here. So let's suppose that I ride my motorcycle down the highway at a constant speed of 75 miles an hour. How many minutes will it take me to drive 20 miles? Now you have a conversion here, and you also have a distance. And I'm asking you to get time out of this. So what I want you to do is fiddle around with the units a little bit and see if you can get from the starting unit to the ending unit. Finding the starting unit is the goal, and that would just be the isolated number. So you're going to be starting with this number. And then what is the question asking you? Find the end unit and solve the question. So I'm going to give you about 3 minutes to play around with this, and then we'll go over the answers together. One more minute, we'll go over the answer. All right, so let's do the same thing here. So I want to find how long it will take me in minutes to drive 20 miles. So my goal is to start with how far I'm going. And I need to figure out how many minutes it'll take me to get there. Well, this is a time. And, oops, this miles is not time. This is a distance. And this is a time. Those aren't the same units, so I'm going to need some sort of conversion to get from distance to time. And fortunately, I have that. I have a distance over time conversion right here. So if I can get to miles, which I start with, I can then turn that into hours. And then if I have hours, I can turn that into minutes. Now, what are my relationships for this? Well, how many miles are there in how many hours? Well, if I'm going 75 miles in 1 hour, every hour that passes, I have driven 75 miles. So if I'm only driving 20 miles, how many hours will pass? A fraction of that. So you should get an answer less than an hour. And then we know that 1 hour is equal to 60 minutes. So let's do the numbers. Well, actually, let's first set up the units real quick. So 20 miles. And then I want to figure out miles per hour. And then hours to minutes. And that will tell me the number of minutes that it will take me to drive this distance. So now let's do the numbers. So there's 75 miles in 1 hour. So 75 actually goes down here because that's where the miles are. And then 60 minutes in an hour. My calculator turned off. And I get 16.0 minutes. But we now need to consider Sig Figs. How many Sig Figs does this have? It has 3. This number right here, however, has 2. This is infinite, this is infinite, this is infinite, because all the rest of this is counted. So, there's my answer. So, this is an instance where one of the numbers that was given to you as a conversion did affect your Sig Fig. So, again, you do have to be careful about it. Alright, we have time for like 1 or 2 more. And then we're going to be done here, so. This is Scoots. Scoots eats 65.3 grams of kibble every day. He's hungry. How much food will Scoots have eaten in 35 weeks? So I'll give you 3 minutes to do this one. We'll go over the answer, and then we'll do Hazel's problem over here. And then we'll be done with chapter 1. I'm going to just leave the rest of it for you to practice. Okay, go ahead and solve this problem, and I'll be back in 3 minutes to go over the answer. One more minute. We'll go over the answer. All right. that's a useful crop there. Here, let me just crop scoots real quick. There we go. Is this helping? Is this helping? No, it's not. Oops. All right, we got to crop scoots out there. So. All right, so we need to find out how much food he eats in 35 weeks. So I know the number of weeks that I'm feeding him. And I want to know how many pounds of food he's going to eat. Now, I have this conversion of grams per day. So if I can get to days, I can get to grams. Or if I can get to grams, I can get to days. Well, I'm starting with a time, which means that if I turn this into days, now I can use the grams per day conversion, and then I can get to pounds. All right, so now let's start writing out some conversions here. So there are 7 days in 1 week. And then he eats 65.3 grams in a day. And then how many grams are there per pound? So I think it's 453.6 grams is a pound. I'm doing that from memory, so. All right, so let's do this. We'll turn weeks into days. So that cancels out. We'll turn days into grams. So that cancels out. And then we'll turn grams into pounds. So that cancels out. And that should give us the amount of food that he eats. So now we do the numbers. So 7 days per week, 65.3 grams per day, and then 453.6 grams per pound. And the result that I get is 35.27. But as people are discovering in the chat, this is only 2 Sig Figs. The rest of these are either infinite or more than that. So our result should only be 2 Sig Figs. So that's how much food he eats in 35 weeks, about a pound a week. So if you buy one of those 20-pound bags of dog food for your puppy, should last 20 weeks, assuming that he doesn't grow, which of course we know is not true. And as they grow, they need more food. If you don't feed them, they stay small, which is cruel. Make sure you feed your animal. All right, last problem we're going to do. This is Hazel. Hazel has a sprained paw, so we took her to the vet. Hazel was my older cat. She was like 22 when she died, which is like ridiculously old for cats. And she was a calico and was adorable. This is not Hazel, but this is the picture of the cutest kitten that I could find. Hazel weighs 2.41 pounds because she is small. And the recommended dose of aspirin for kittens is 3.67 milligrams of aspirin per kilogram of body weight. How many milligrams of aspirin should be given to Hazel? So I'm going to give you 3 minutes to do this. We'll go over the answer. We're going to talk about what happens for the quiz for chapter 1, and then we'll be done. Okay, so go ahead and do this problem. And stare at this adorable kitten. We're actually almost out of time, so I'm going to start the problem now. So let's do this. So I've already set up the units here. If you know how much your cat weighs, you can then turn that to kilograms and then convert that to milligrams of medication per kilogram of cat body weight. So I'm going to start with the amount of pounds of cat that I have. And then I know that there are in 1 kilogram 2.205 pounds. And then I also know that per 1 kilogram of cat, I can safely give 3.67 milligrams of aspirin. So let's do the let's do the units first, and then we'll do the numbers. So we'll do pounds of cat to kilograms of cat. And if you aren't sure, you could always just write cat after this, just to keep your information organized. And then for kilograms cat, we can convert that into milligrams of aspirin. Oh, I canceled the cat. I feel bad. All right, now I can do the numbers. 1 kilogram is 2.205 pounds. And there are 3.67 milligrams per kilogram of cat. And the answer that I get is 4.01 milligrams. And then finally, we check for Sig Figs because you don't want to over-medicate the cat because you had the wrong number of Sig Figs. That's unlikely, but anyway. 3 is the lowest, so our answer should have 3 Sig Figs. All right. You can't see all that. Let me just scroll that on the screen. There we go. All right, really quick, back to the lecture slides. There are extra slides here. Oops, that's the wrong one. So I have this. I was playing Dragon Quest XI, I think, when I wrote this slide. There are extra problems for you to try, which have conversions at the bottom. And then there's a last little bit about temperature. I'm not going to have enough time to do the temperature joke, unfortunately. But you can read about temperature. You can see that there is very clearly a letter missing in this space if you just go left to right here. And that's because that's the temperature scale for the absolute scale for Fahrenheit. Just like Kelvin is the absolute scale to Celsius. I'm sure everybody knows about the relationship between absolute zero and temperature right now. But just in case you didn't know, what letter should go in the blank? Obviously, it's the letter R. There it is. Oh, it didn't buzz because I don't have the volume on there. There you go. Since everybody's thinking a different letter, that letter is wrong. So we're not going to actually use Rankine ever. And in fact, we're going to try and avoid Fahrenheit. These are the two that we're going to use. But for the most part, Kelvin is the important one by far. And then I'm going to give you the formulas to convert between those. You may actually see something that looks like this. So if I took this top one right here, it would be 9 over 5 times Celsius plus 32. Just be mindful that 9 over 5 is just 1.8. So I am typesetting my formulas in a different way so that I can actually get it on one line. So if you look up the formula and you're like, oh, it's a 9 over 5 or 5 over 9, but your formulas didn't have that, they're both the same. Don't worry. I've already accommodated for that. All right. That's chapter 1. Sorry to rush at the end there. At the end of each set of slides, there is a summary page here that just goes over them. So if you are looking at what will be on your quiz, the first place that you want to do is go to the summary at the end here. Oops, I thought that went back to the first page there. So like section 1, when we talk about the scientific method, those are the important topics. We talked about classifying phases of matter. Those are the important topics. So if you know all these things, there are a lot of things. This is why this chapter took 2 weeks. If you know all of these things, you will do just fine on the quiz. Okay. All right. So what does that mean for the quiz? So when we go back to the calendar here, after today's class, what is going to happen is there will be a quiz will appear on the schedule. And so when I hit the button and release the quiz, it will be available. You'll have a week to do the quiz. That means that since today's the 14th, quiz number 1 will be due the 21st. And we can even type that down here at the announcement. And, oops, that's the wrong button. There we go. We can even type that down here. So we'll go boop, boop. So quiz number 1 due, and that's Wednesday, 21 April. There you go. So that is now on the announcements. You're going to see that next week until that expires and falls off of the scheduler. But yeah, you'll have the first quiz available. You get 2 attempts. I do not release the scores until everybody has completed the quiz. So please don't email me asking, hey, I didn't know if I got a high enough score. Do I have to take it again? If you weren't sure, take it again just as insurance. If you feel confident, you only have to do it once. Otherwise, you can use any resource you want except me. I cannot answer any questions about the quiz. So if I start seeing questions about Mani the Orc weighing his pile of treasure chest gold, I will know. No, I can't answer that question. Sorry. Okay, but I will answer other questions. So let me know either over email or Discord if you have any questions about either the lab or class content or whatever. We're going to start Chapter 2 next week. Chapter 2 is a bit of the philosophy behind chemistry and how everything got started. We're going to dive into the nature of atomic matter and look at experiments that people did and show some YouTube videos about that too. So thanks for watching the lecture. Have a wonderful weekend. Make sure you take quiz number 1. Make sure you do lab number 1. Get all that stuff in. And then go out and enjoy some sun. Get some rays.